Hello, I am going to teach you module 11 lecture 3, which is the complementary filter. The complementary filter is coming from an aspect where you use your high pass filter and the low pass filter as told by Dr. Vishwanath. So, I will be continuing on that on the implementation of the complementary filter. We have already seen the aspects of jitter, of drift, jitter in the accelerometer, drift in the gyroscope. So, we see how we can implement the complementary filter to reduce the drift and the jitter. So, what is sensor fusion? Sensor fusion is a technique where we use multiple inputs, we fuse the data to get a particular variable out of it. So, for example, over here if you see that there is an IMU, there is a GPS and there is a camera. As Professor Vishwanath has already spoken to you about celestial navigation with dead reckoning, that technique where you fuse the data from the dead reckoning sensors and the celestial navigation. So, we use some block called the sensor fusion block where we add these two sensors to get a particular output. Here I am going to show you the fusion between the accelerometer and a gyroscope. Okay, why do we need sensor fusion? As we can see over here, the angle which is computed here can be used directly from the accelerometer by passing this angle information, which uses the accelerometer values to calculate the angle. So, this is the formula where we calculate the angle from the accelerometer. It is a tan 2 of the axle x. I will tell you the explanation. A tan 2 of axle x divided by square root of axle y into axle y plus square of axle z. So, if we consider an accelerometer to be this duster, we have the x axis which is facing towards us, the y axis which is facing parallelly to us and the z axis which is facing downwards from us. So, if this is the accelerometer that we are considering, x is always the forward axis, the y is the parallel axis and z is the perpendicular axis to the body of the accelerometer. So, if we want to find out an angle, for example, the pitch angle which is supposed to be like that, a movement which happens upwards in this direction, we consider axle x to be the forward direction axis, the axle y which being this axis and the z axis which is perpendicular to the axis of the accelerometer. So, we get meters per second square and g values from the accelerometer. G basically is a g force. So, if I consider an accelerometer to be stationary like this in air, the x axis which is parallel to the ground and the y axis which is parallel to the ground does not measure any acceleration, but the z axis which is measuring the gravity is measuring 9.8 meters per second square. So, we call that to be g and we normalize the value of 9.8 meters per second square into a g value. So, you get plus or minus 1 g depending on the orientation of the sensor. So, the accelerometer value that we get as g is passed through the angle computation block. So, the angle computation in this block, when we get the g value, performs a certain function which is mentioned over here. This angle computation is then passed. So, we get a value of theta accelerometer. So, this theta accelerometer is passed through the low pass filter, which is removing all the high frequency noise. As we know that the accelerometer has a lot of high frequency noise, we can remove it by designing a customized low pass filter for this particular function, where this low pass filter reduces the jitter from the accelerometer data. So, the value we get over here is theta low pass. So, this is the angle that we get from the accelerometer. Similarly, we can do the same from the gyroscope. So, from the gyroscope we can compute the angle. The gyroscope basically gives you a value in degrees per second, so which is your angular velocity. This value from the gyroscope, which is degrees per second, is passed through the numerical integration which is shown as a function over here. This is a Matlab function where we pass the gyroscope in through the numerical integration by gyro into time I minus time I minus 1 and add it with the previous angle of the gyro. So, this is the function of a numerical integration. So after we compute the numerical integration of the gyroscope value, we get an angle which is theta gyroscope. So, as Professor Vishwanath has already mentioned that the gyroscope values have after integration give a lot of drift. So, the drift is compensated by passing this angle through the high pass filter. So, the high pass filter basically cuts off the low frequency noises, which is the drift, and gives you a value theta high pass value, which is again the angle. So, now that we know that we can compute the angles from the accelerometer and the gyroscope, we tried to fuse these two sensors, which is your accelerometer and your gyroscope, to compute the angle for better performance. So, now we can see here that the accelerometer giving values in meters per second square and gyroscope giving values in degrees per second. The accelerometer is passed through the angle computation and the low pass filter. The gyroscope is passed through the numerical integration and the high pass filter. Both of these, which is the theta low pass and the theta high pass as shown previously, is then added and then we get the angle. So, why do we use a low pass filter for the angle calculated from the accelerometer? So, now that we know that the angle can be calculated from the accelerometer and this has to be passed through the low pass filter, I will tell you why the low pass filtering is required. If we consider this to be the accelerometer, we keep it stationary on the ground, we can get data which is very similar to this. So, we get a very stationary data which is around 83 degrees. So, the data we receive over here is at a mean of 83 degrees, but it has a lot of jitter. So, it varies from around 82 degrees to around 85 degrees, 84 degrees. So, we need to pass it through a low pass filter to remove the high frequency components. So, the red graph which is over here is the high frequency component jitter that we get when we calculate the angle from the accelerometer. We pass the high frequency component through a low pass filter with a certain cutoff frequency. So, this cutoff frequency can be calculated in such a way that the jitter which we see in the red graph can be removed, and we calculate in this particular experiment to be 3 hertz. So, this frequency, that the cutoff frequency that we calculate, gives us a response which is in the yellow form. So, yellow form is the filtered out data and the red is the raw data. So, now we can see that when the accelerometer is kept stationary on the ground, we get a better curve which is centered at 83 degrees. So, now I will be showing you why we use the high pass filter. So, the gyroscope data that we have, which is denoted by omega, is in degrees per second. So, once this omega is passed through the numerical integration, we get the value of angle which is theta of the gyroscope. So, this value is then passed through the high pass filter, and now we get theta high pass. So, after getting the value of theta high pass, we see the experiment which is conducted using the L3G4200D, which is a 3-axis gyroscope. If we consider this to be our gyroscope and keep it stationary on the ground, we see that we get a drift. So, this drift is basically the drift where if we need to integrate our omega plus noise, So, the noise also gets integrated when we trying to integrate the gyroscope value to find out theta, and hence this causes a drift. So, this drift can be seen in this particular experiment where we use a 3-axis gyroscope, and the blue line is the angle from the raw gyroscope, and the black line which is above over here is the angle passed through the high pass filter. So, now we see the response of the high pass and the low pass filter. The high pass filter, which is on the left side, has a response which is like this, where the Fc is the cutoff frequency of the high pass filter, and you have a pass band from Fc to infinity. So, now we look at the low pass filter, where the low pass filter has a frequency response which is similar to this. There is a decay after the Fc, which is your cutoff for the low pass filter. So, if I consider a frequency, for example, as 3 Hertz, so after 3 Hertz there is a 20 dB slope decay in this response. So, the pass band is basically from 0 to 3 Hertz. So, now what is the complementary filter? The complementary filter is the combination of the high pass filter and the low pass filter. So, let us consider the angle theta true. This is measured from both your sensors, as we know from the accelerometer and from the gyroscope. So, this angle, which is the truth angle, is measured from your accelerometer and the gyroscope using their computations. The angle, which is theta axle, is passed through the low pass filter, and the angle, that is theta gyro, is passed through the high pass filter. So, we have seen already why we pass the accelerometer angle and the gyroscope angle through the respective high pass and the low pass filters. This angle, which is low passed and high passed, can be called as theta low pass and theta high pass, is passed through a combination of the high pass filter and the low pass filter. So, I will show you the combination of the low pass filter by taking the cutoff frequency as 3 Hertz. So, if I consider 3 Hertz cutoff frequency, I have a response of my low pass filter which is like this, and the response of my high pass filter which is like this. So, essentially if I pass the theta low pass and the theta high pass through the complementary filter block, I will get an output which is having a response with a magnitude of 1. So, the y axis is the magnitude and the response is always 1. So, at the output we get theta true. So, for example, if my theta true is a lower frequency signal, we can see that the low pass filter actually weighs more in this complementary filter. So, if my signal comes in this region, my low pass frequency, the low pass filter basically dominates over the high pass filter to give the magnitude as 1, and if I get a higher dynamic frequency which is in this region, my high pass filter takes over and the output from the high pass filter weighs more in the magnitude of 1 to measure the theta true. So, now I will be taking you through the design steps of the complementary filter. So, we basically know that the complementary filter algorithm helps to get us better accurate angles and accurate computations. So, I will be taking you through the design steps of the complementary filter. So, just to revise back the block diagram of the complementary filter, this is the complementary filter where the accelerometer, which is present over here, it gives you a value in meters per second square. The gyroscope, which is present over here, it gives you values in degrees per second. So, right now we know that the accelerometer is giving acceleration data, the gyroscope is giving me angular velocity in degrees per second. We pass the accelerometer data through the low pass filter. Here is the low pass filter where we have already discussed what the low pass filter does, and then we pass it through the angle computation block where we get theta of your accelerometer. Now, we already know that from the gyroscope we can also get the angle by numerically integrating the values of the gyroscope. We get the angle theta gyroscope over here, and we get theta gyro high pass. So, these two angles that we have, that is your theta acceleration and theta gyro high pass, has to be added together in the complementary filter block with the respective weights, and we compute the angles from that. So, going to the design steps of how we design the complementary filter. So, we know that the gyroscope and the accelerometer are the sensors which we are using. So, it is very essential to see the data sheets of these sensors, because the sensors are the main part in the acquisition of the data. So, here once we see the data sheets of the accelerometer and the gyroscope, we get the values of the bias, and also we get the random noise which is present while we are doing data acquisition. So, then we carefully choose the cutoff frequency. The cutoff frequency Fc, which is mentioned over here, is to be chosen based on basically 3 parameters. If you see the note below, the cutoff frequencies are chosen depending on the frequency of movement, that is how fast your actual movement is happening, and the noise, that is the jitter present in the accelerometer. As shown previously, there is a lot of jitter present in the accelerometer, and then also the frequency of the drift which is present in the angle computation when we compute the angles from the gyroscope. So, now that we have chosen the cutoff frequency, we know the formula for cutoff frequency and the time constant. So, the cutoff frequency over here has the formula which is like this: Fc is equal to 1 by 2 pi Rc. Now, depending on what cutoff frequency we choose, we can find the value of tau. So, tau is basically R into C, that is, if you reframe the first equation which is above, Rc is equal to 1 by 2 pi Fc. So, now we have the values of Fc and we have the value of tau. So, next we see how we put these values of your tau and your cutoff frequency to design a low pass filter. So, as you see on the left side, there is a circuit which is the low pass filter. You have the Vn over here, we have the R and the C circuit. So, this is a passive low pass filter. So, now we know that from previous lectures that if Vin is considered as x and V out is considered as y, we get this equation of the low pass filter, where y of I is equal to x of I, which is your input, into delta t. Delta t is basically your sampling rate. So, delta t is your sampling rate, and we know the value of Rc, which is equal to tau again plus delta t plus y of I minus 1. So, this y of I minus 1 is the output of the previous function. So, y of I minus 1 into Rc divided by Rc plus delta t. So, now with this equation we can get a simplified equation of the low pass filter, which is in the corner below here. Y of I is equal to alpha low pass into x of I plus 1 minus alpha low pass into y of I minus 1. So, this is the simplified equation of a low pass filter, where alpha low pass is given by the equation delta t divided by Rc plus delta t. So, with this we get, from the previous slide we have seen that we get Fc, we get the value of tau, and now we have the value of the alpha. Let us move on to designing the high pass filter. So, the high pass filter circuit is shown over here, where V in is here, your capacitor and your resistor, and this is a passive simple first order high pass filter. So, previously we have seen the equations of this high pass filter to be y of I is equal to y of I minus 1 into RC divided by RC plus delta t plus x of I minus x of I minus 1 into RC divided by RC plus delta t. So, this equation can also be simplified and written as y of I is equal to alpha high pass into y of I minus 1 plus alpha high pass into x of I minus x of I minus 1. So, here we know that the input again is considered as x and the output is considered as y. So, with this equation we get the filter coefficient, that is alpha high pass is equal to RC divided by RC plus delta t. So, now for the high pass filter we have the cutoff frequency, we have the value of the time constant, and we have the value of the alpha high pass filter. So, now we have seen that for the low pass filter and the high pass filter we have the parameters which are stated here. We have to combine these two filters together to make something called a complementary filter. So, I will be showing you a Matlab implementation of the low pass filter. So, if you see over here, if you remember from the block diagram, the accelerometer values, which is coming as meters per second square, is passed through the low pass filter and we get the value of LPF over here. So, we know that we are using a 3 axis sensor which is x, y and z. So, hence we get LPF underscore x, which is your low pass filter of the x axis, LPF underscore y, which is the low pass filter of your y axis, and LPF z, which is the low pass filter of your z axis. So, we pass this through the equation which is shown here. I will be giving you the Matlab implementation, the complete file, which includes the low pass filter application, which also includes the high pass filter application and also the complementary filter implementation. So, now we see that after we pass the values that we get from the accelerometer through the low pass filter with the equation which is shown over here, we can see that the values are more stable. There is less amount of jitter present in your accelerometer. If you see the graph on the right side, the red graph is basically a raw acceleration value, which is again in meters per second square, or you can consider to be g, where g is equal to 9.8 meters per second square. So, your raw acceleration value, which is the graph which is in red, is more jittery compared to the axle passed through the low pass filter, which is in black. So, we see over here that once we pass it through the low pass filter, the mean of this whole line is very close to 9.8 meters, 0.98 g, but otherwise when we do not pass it through the low pass filter, as we see in the red graph, it varies from 1 to 0.96. So, we see that we get more accurate data when we pass it through the low pass filter. So, this is the data when the IMU which is present, which is your sensor, is kept stationary. Now, we will see an implementation where your IMU is actually moving. So, over here again we have the same color combinations, where the red graph is your raw acceleration value. Consider this to be your accelerometer. We have an accelerometer which is kept on my hand, and I move the accelerometer from 0 degrees to 90 degrees and back to 0 degrees. So, this is the graph that I do get when I move the IMU, which is my accelerometer, over here from 0 degrees to around 80 degrees for example, and the red graph if you see has a lot of jitter. So, we pass it through the low pass filter where the axle values are passed through the low pass filter and is marked in black. So, we see that the black line is a more smoother line compared to the red line. So, now we will see the Matlab implementation of the high pass filter. So, we know that when we calculate angles from your gyroscope where the angle underscore gyro is the computed angle. So, here we have angle underscore gyro which we then pass it through the high pass filter. So, we know the equation of the high pass filter which is previously shown. So, we pass the angle underscore gyro through the high pass filter where the equation is shown over here as well, and we get HPF, so the value of HPF. So, this HPF value is the value which we are getting after we pass the angle computed from the gyro through the high pass filter. Here on the right side we can see a graph which shows the component of drift. So, if you see over here the IMU is kept stationary on the ground, you see that this is the stationary data. We always want the angle to be constant. So, we keep it at around 0 degrees. Because of this integration there is a buildup of noise, and then we see that the angle which we are computing, this the y axis is the angle which we are computing from the gyroscope is always drifting. So, at around 8000 samples we are getting around 90 degrees of drift. So, we see that there is the angle which is not stationary, but the noise which is building up causing the angle to be drifted. So, now when we pass this angle through the high pass filter, it does not allow changes as spoken previously and gives you a line which is the black line. So, this black line is the line where when we have a stationary value, when it passes through the high pass filter we get almost a straight line. So, from this we get to know that we need to remove the component of the drift in your angle computed from the gyroscope and your component of jitter from the accelerometer. So, this can always be done only by the good selection of your FC, which is your cutoff frequencies. So, if your frequencies are not chosen properly, your angle which maybe that your angle which you are calculating is drifting away, or your jitter which is the component present, which is the component of noise present in your accelerometer, does not get removed properly. So, here is another Matlab implementation of the high pass filter. So, on the y axis we have angles again which is computed from your gyroscope, and your x axis is your data samples. So, we see over here again we conduct an experiment where the IMU is present on the hand. We move from 0 degrees to 80 degrees and back, and we continuously repeat it for 7 times. So, we see that there is a graph which is coming, which is your blue line, the raw angle which is calculated from your gyroscope. So, we see that the blue line over here has a lot of drift. If you can see, I am doing an experiment where I am going from 0 degrees to 80 degrees and coming back to 0 degrees. So, this experiment which I am doing has a lot of drift, where for example, after 9000 samples I am getting it to be around 70 degrees. So, which is this value of around 70 degrees is not correct, because I have stopped the experiment at 0 degrees. So, hence I pass this through the high pass filter, which is your black line again over here, and I get a data where at 9000 samples I am almost at 0 degrees. So, you will say that there is an issue with this graph, where for example, the data which we are computing in the blue line, which is your angle computation from the gyroscope, has a bigger magnitude than the magnitude present over here in the black line. So, your magnitude present over here is larger than the magnitude which is present in your high pass filter. So, now I will explain why we get this value. I will just draw a filter response, the frequency response of this high pass filter, taking the cutoff of Fc. So, in your blue graph, we have some data which is being removed because the high pass filter is designed in such a way that the Fc is also removing some part of the signal. So, for example, the signal which we are getting is around this range. So, anything which is below the Fc is being rejected, and only the signals which is on the right side of the Fc is being passed. Hence, we see that there is a drop in the magnitude in this graph as compared to this graph. So, this is very important when we choose the cutoff frequencies of your high pass filter. We do not want the signal also to be removed, we just want the drift to be removed over here. So, what do we do? So, what do we do over here? So, now that we know that this is my Fc which is chosen in this graph, I want to choose an Fc which is much lower, which comes somewhere to the left towards 0, so that my filter response looks like this, and the signal which is present in this area is also passed through. So, I will be showing you an implementation where we have actually changed the Fc, we have made it a lower Fc, so that we get better values of the signal. So, on the right side, if we see over here, if we see over here, the magnitudes of the blue line and the black line is very similar, only that the component of drift is being removed. So, here we have chosen an appropriate Fc such that we do not reduce the magnitude of my response. We have already seen from the previous examples as to how to calculate the angle. This is a Matlab implementation of how we calculate the angle from your IMU. From the accelerometer, we calculate the angles in this manner. So, we take this equation and we get the value of the axle. So, this axle angle is got from this equation which is above. From the gyroscope, we pass it through the numerical integration, and then from the gyroscope we pass it through the numeric integration, we get the angle gyro, and we pass it through the angle gyro high pass to get the angle in the output. So, here is how we calculate the angle from the gyroscope. This is also shown previously. So, this is a repetition of this, and now we pass this through the block of the high pass filter to get angle underscore gyro underscore hp, which is this. Complementary filter is a filter in which we combine these two angles, that is your angle accelerometer and your angle gyro hp, with certain weights to get an output response which comprises of the true signal. So, the complementary filter, as we know, follows this equation where the angle from your complementary filter is equal to alpha Cf, which is your filter coefficient of the complementary filter, into the angle that we get from your accelerometer, plus 1 minus alpha Cf, which is again your filter coefficient of the complementary filter, into the angle we compute from the gyroscope after passing it through the high pass filter. So, now we need to choose the value of alpha Cf. So, how do we choose the value of alpha CF? So, if you can say that the frequency of motion of, for example, you are trying to measure a certain movement. For example, I am just moving my hand from 0 degrees to 90 degrees again and back. So, you actually want to see what is the frequency of motion over here, and from the frequency of motion we decide to give weightage to either the accelerometer or give weightage to either to the gyroscope. So, we see that we are moving the IMU from 0 degrees to 90 degrees and back to 0 degrees. We see the frequency of movement of this hand, which is measured by your sensor, and if the frequency is lower, we give more preference to your accelerometer. If your frequency of motion is higher, we give more preference to the gyroscope. Here alpha CF is in between 0 to 1, where if we give the value of alpha CF is equal to 0, the angle from the gyroscope is dominant, or if we give alpha CF is equal to 1, angle computed from your accelerometer is dominant. So, we need to choose a value of alpha CF depending on how fast or how slow we are moving. So, after we choose the filter coefficients of the complementary filter, we see that your low pass filter will give a response which is similar to this, and you can say this is my FC, and my high pass filter will give a response which is similar to this. So, now that we are getting a response like this with the same FC, we know that we will get a response of magnitude of 1 when we pass the signal through the complementary filter. So, now we will be discussing a small problem on this design of the complementary filter. Here consider an induction motor which is rotating at 1100 rpm. 1100 rpm is equal to 6600 degrees per second. So, 1100 rpm is equal to 6600 degrees per second, which is approximately equal to 18 hertz. So, we know that the equation for calculating from rpm to hertz, we get 1 rpm is equal to 1 by 60 hertz. So, if we get 1100 rpm, then 1 by 60 into 1100, we approximately get 18 hertz. So, we consider the value of 18 hertz, which is your frequency of your message signal, and we strap on an IMU to calculate the angle of this motor shaft. So, we have an accelerometer and a gyroscope which is present on the motor shaft, which is computing the angles of the motor shaft. So, we know that in this problem we have already been given the value of FC, which is FC is equal to 20 hertz. So, here we need to design a low pass filter and a high pass filter to combine them together to get a complementary filter. We have also given the value, which is an assumption, that C is equal to 1 microfarad and your sampling rate, which is f of s, is equal to 50 hertz. So, we know the equation of f of s and delta t, where delta t is equal to 1 by f of s. So, now f of s 1 by 50, which is equal to 0.02. So, over here if I have to just mark my parameters that I have, I get Fc is equal to 20 hertz, your value of delta t is equal to 0.02 and the value of C is equal to 1 microfarad. So, now we will see how to design the low pass filter. So, we know that your value of Fc is equal to 20 hertz. So, we need to design a high pass filter and a low pass filter for the same cutoff frequency, and we also we need to find the value of tau, which is your time constant, where tau is equal to R into C, where your sampling rate is 50 hertz. We know the equation of tau, where tau is equal to R into C, which is again equal to 1 by 2 pi Fc, which is equal to 1 by 2 into pi into Fc, which is 20. We get the value of tau to be 0.079579. So, now we know the value of tau, which is equal to 0.00795. After getting the value of tau, we calculate the value of R, where tau is equal to R into C, R is equal to C by tau, and we put 1 microfarad divided by 0.00795. So, your value of R comes to 7.95 kilo ohms, which is given over here. So, from this problem we have found out a few parameters, which is your Fc, which is your delta t, your C, your tau and R. With this parameters we start to design the filter. On the left side, if you see, it is the filter circuit of the low pass filter, and on the right side we see that it is a filter circuit of the high pass filter. So, we know the values of R, which is 7.95 kilo ohms. I mark it on the right side as well, 7.95 kilo ohms, and C, which is 1 microfarad, and C, which is 1 microfarad. So, we have actually completed the first question, where we have designed the low pass filter circuit and we have also designed the high pass filter circuit. Now, we need the values of alpha. So, now on the left hand side we want to find the value of alpha low pass, where we can put it into the equation. So, the value of alpha low pass, if you remember the equation, is equal to delta t divided by RC plus delta t. If I have to rewrite that again, 0.02 divided by 0.00795 plus 0.02. This is your value of alpha low pass, where you get alpha low pass is equal to 0.7155. So, this value of alpha low pass, you can put it into the equation of your low pass filter, where y is your output and x is your input. So, from this we have actually got the equation of your low pass filter. Now, we move on to the high pass filter, where the equation for calculating the alpha high pass, which we want to put it into the filter equation. The formula for alpha high pass is equal to RC divided by RC plus delta t, which is 0.00795 divided by 0.00795 plus 0.02. So, if we calculate the value of alpha high pass, we get the value 0.2844. We put this equation into the equation of the high pass filter, where y of I, y is your output and x is your input. So now we have designed basically two circuits, which is your passive low pass filter circuit and your passive high pass filter circuit. Next, we have also calculated the value of alpha low pass and the value of alpha high pass, and also put it into the equations of your low pass filter and the high pass filter. Now we move on to finding out the transfer function of these two filters. So now we know the value of R is equal to we know the value of R is equal to 7.95 kilo ohm, and the value of the capacitor is 1 microfarad. Similarly, over here 1 microfarad and 7.95 kilo ohms. So we already have studied, Professor Vishwanath has taught you about the transfer functions of these filters. So we know the transfer function of the low pass filter, which is given over here. H of S low pass filter is equal to 1 divided by 1 plus RCS. So we know the value of RC, where tau is equal to RC is equal to 0.00795. So we get the transfer function of your low pass filter to be 1 divided by 0.00795 S. So now we know the transfer function of the high pass filter, where H of S HPF is equal to RCS divided by 1 plus RCS, where again RC is your tau, which is equal to 0.00795. So we get the value of H of S high pass filter is equal to 0.00795 into S divided by 1 plus 0.00795 into S. So this is the transfer function of your low pass filter, of your high pass filter, and on the left side is the transfer function of your low pass filter. So now we have come from the cutoff frequency, we have calculated your RNC values and your tau values, and we have also calculated your alpha values, put it into the equation of the low pass filter and the high pass filter, and we have come to get the transfer function of the low pass filter and the high pass filter. After we have the transfer functions of the high pass filter and the low pass filter, we now find out what is the corner frequency, because with the corner frequency we can get the Bode plot. So we can draw the Bode plot by using the corner frequency, which is omega c, which is in terms of radians per second. So now that we have got the equations, I will again input the values of R and C. R is equal to 7.95 kilo ohms and C is equal to 1 microfarad and 7.95 kilo ohms. So these are the two equations where we calculate the corner frequency, which is omega c. Omega c is equal to 1 divided by RC, which is omega c is equal to 1 divided by 0.00795. When we do this equation, computation, we get omega c is equal to 125.786 radians per second, which is the same for your high pass filter as well. So your omega c for your high pass filter and your omega c for your low pass filter are the same, where both omega c is equal to 125.786 radians per second. So now with the transfer function, there is all in the implementation of the Matlab code that we will be giving it to you. We have also shown the Bode plot. So with the transfer function you can actually draw the Bode plot, or in a freehand drawing you can draw the Bode plot of this by in this manner. So 125.786 is your 3 dB margin, which comes over here. So over here you get the value of omega c in radians per second. So we know the corner frequency of this Bode plot, where omega c is equal to 125.786 radians per second. So, here are the Bode plots of the low pass filter and your high pass filter. It follows the curve as shown here and it follows the curve as shown over here. So, with this we have actually designed the low pass filter and the high pass filter and also got your Bode plots. So, just to revise, just to summarize on what steps we have taken. Steps for design: can be written like this. So, we choose the values of Fc, then calculate the tau, where tau is equal to R into C. Next, we get the values of R and C and input into the circuit respectively for the low pass filter and the high pass filter. After we get the circuit, we calculate the values of alpha low pass and the value of alpha high pass filter. So, these are the filter coefficients. We put it into the equations of low pass filter and high pass filter. After we get the equations of the high pass filter and the low pass filter, we get the transfer functions of these two filters. Once we get the transfer functions of these two filters, we get the Bode plots of these two filters. So, we have actually completed the design of the low pass filter and the high pass filter. Now, we will see how to combine these two filters to get the complementary filter. If you remember the block diagram, we had axial values, which is meters per second square, your gyro values which you are getting in degrees per second. So, this axial value is passed through the low pass filter and you get the value of axial low pass. From the value of axial low pass, we pass it through the angle computation block which is shown previously and we get the value of theta low pass. So, this is the theta, which is the angle got from the axial value passed through the low pass filter and gone through the computational block for calculating the angle. Now, we go to the gyroscope, where the gyroscope is passed through the numeric integration and we get the angle theta gyroscope. This gyroscope, theta gyroscope, is passed through the high pass filter and we get the value of theta high pass. Now that we have the value of theta high pass and theta low pass, we combine these together with weights of alpha Cf and 1 minus alpha Cf to get theta Cf, which is your complementary filter. So, here is a complete design of the complementary filter. You can actually implement it if you have an accelerometer which is interfaced and a gyroscope which is interfaced. You can rig up a circuit which is similar to this on the top, where you have a low pass filter with a resistor and a capacitor. You pass in the input from the input end and you get the output from the output end. You can pass this block through an angle computation block which is shown previously to get theta low pass, and you use the value of alpha Cf to pass it into the complementary filter. So, from the gyroscope you can actually do something like a numeric integration. You will get the value of theta gyroscope. You can take this value and rig up a circuit for the high pass filter, where your capacitor is 1 microfarad and your resistor is 7.95 kilo ohm, approximately 7.95 kilo ohm, and you will get the value of theta high pass. You can use this theta high pass which is multiplied by this weight, which is 1 minus alpha CF, and also put it into the complementary filter. So, this is how you can implement a complementary filter in real time. So, now we have shown the implementation of the complementary filter and how to actually design it from end to end, from choosing your cutoff frequency and coming to your Bode plots, and also integrating these two filters, which is your low pass filter and a high pass filter, to get a complementary filter. In the forum, we will be having some reference material. As some of you all would like, we are going to give you an Arduino code which interfaces an IMU, which is basically considering a GYIT. This is the sensor that we have chosen. This GYIT consists of an accelerometer, a gyroscope and a magnetometer. We will be giving you the codes where the GYIT will be computing accel values and your gyroscope values. So, this accel values and the gyroscope values will be printed on serial monitor. You can actually interface it to Matlab or something like that, where in our Matlab code we will also have an option where this serial data that we get from an actual sensor, which is your GYAT, will be taken into Matlab, which will read the data from these accel, or also read a data from the CSV file. The choice will be given, where two different Matlab codes for either reading the data or directly receiving the data, taking the data from a CSV file will be given. We will be able to plot the raw data, which is your accel values, your gyroscope values. We will be showing you the filtering techniques, which is your high pass filter and the low pass filter, and also plotting it. And we will be showing you in another file, which is the complementary filter equation for implementation of the complementary filter, and also plotting the angles which we get from the complementary filter. I hope you guys have enjoyed this course. This was a practical implementation of the complementary filter. As I said, the reference material will be given, and if you require any help, please feel free to ping me. Thank you.